In this tutorial, we are going to learn about potentiometers. Potentiometers are found everywhere, in electronic circuits, in your car, whenever you adjust the volume of your radio, in fans, whenever you adjust the speed of a fan that you have at home, and in many other devices. Potentiometers are variable resistors. In other words, we can change their resistance based on a mechanical action. What we have in front of us right here is different types of potentiometers. For example, right here, we have a rotary potentiometer, which means that we can turn the knob clockwise and counterclockwise in order to adjust the resistance value. Also, we have a linear potentiometer. In other words, I can slide this potentiometer left and right, or the slider right here, in order to change its resistance. Also, we have another type of a potentiometer, which is also a linear potentiometer, and by sliding our finger on the potentiometer right here on this strip, we can change the resistance, as we will see later on. So these are various types of potentiometers, and usually in a potentiometer, we have a resistive element that we change its effective lengths. So we can see right here, it's visible. We have a resistive track that we will see shortly. And by sliding the slider over this resistive track, we can change the resistance. So as you can see, we have an Arduino UNO connected to a potentiometer right here. In series to this potentiometer is connected a 1 kilo ohm resistor. So let us just see it clearly in order to see the colors. And this resistor in turn is connected to our Arduino UNO. So we will see the details of the circuit shortly in order for you to be able to reproduce it. And we will see later on how we can control the brightness of this LED through this rotary potentiometer. So let us go ahead and check what we need for this tutorial in terms of hardware. So as usual, we need an Arduino UNO R3, some fixed value resistors, specifically a 1 kilo ohm resistor. We need a rotary potentiometer. Here we have a 10 kilo ohm rotary potentiometer. We need a power supply, a breadboard on which we will assemble our circuit, some electric wires, along with a USB cable to connect our Arduino UNO to the PC or laptop, and finally some colored LEDs. So let us go ahead and check again our potentiometer. As we can see here, we have a 10K value written on this rotary potentiometer, which means that its resistance changes between 0 and 10K, as we will see shortly. So, as we said, a potentiometer is a 3-terminal resistor with a sliding or rotating contact that forms an adjustable voltage divider. So we are going to understand what's a voltage divider in this tutorial, how to derive its equation, and how to manipulate it in order to get the resistance value as well. So a potentiometer has 3 terminals, one to be connected to the ground, one to be connected to a power source, and one for the voltage or resistance output, as we will see shortly. 2 of the terminals are connected to the opposite ends of a resistive element, and the 3rd terminal connects to a sliding contact or a rotating contact as well. Potentiometers, as we said, are commonly used to control electrical devices such as volume controls in audio equipment and also for speed control in fans. Also, they are found in electronic circuits whenever we want to have an adjustable voltage or a variable resistance. In addition, they are used in sensors as a mean to control or adjust the sensitivity of a sensor. So let us go ahead and check what's inside a potentiometer in order to understand its structure, how it works, and why it has 3 terminals. So as we can see right here, we have the common type, which is a rotary potentiometer, as we mentioned at the beginning of the tutorial. And let's see what are the main components of this potentiometer. First of all, we have the housing of the potentiometer. This is the structure holding everything together. On it, we have a resistive strip or a resistive track. And this is the resistive element that is essentially used in order to have a variable resistor or a potentiometer. On it, it sits a wiper, which is the rotating element. And this wiper can be rotated clockwise and counterclockwise. Now notice here how this wiper touches the resistive strip. So by rotating this wiper clockwise and counterclockwise, we can change the effective lengths of the resistive track. In other words, the distance between this point here, which is the first terminal, and the contact point here between the wiper and the resistive strip or track. And notice here how the two ends of the resistive strip are connected to the first terminal and the second terminal. So the first terminal of the resistive track, for example, is connected to a voltage source, let's say 5 volts in this case, because we will be connecting it to the Arduino UNO. And the second terminal is connected to the ground. Now the middle terminal, which is directly connected to the wiper, and the wiper directly touches the resistive track, is connected to an output pin or an analog input pin on the Arduino UNO, as we will see shortly. And by rotating the wiper clockwise and counterclockwise, what we are doing is we are changing the effective lengths right here of the resistive strip, and therefore we are changing the voltage between this terminal right here, which is Vs, where we are supplying the voltage, and the output terminal right here. And therefore we can have a variable voltage, or in other words, a variable resistance that we can measure. Now for rotary potentiometers, usually we have two types. We have B types, which means they are linear taper, and we have A type, which means they are logarithmic taper. What does that mean? Let us go back and check this potentiometer right here. Here it says B 10K. First of all, 10K means that the upper range value of the resistance, or the largest value, is 10 kilo ohms, and the lower value is logically 0 ohms. But ideally it can't be 0 ohms because we will have still some resistance in the wire or the wires and the resistive strip as well, as we will see shortly. Now B stands for a linear taper, which means there's a linear relationship between the input and the output. Let us go back to our slides to check what does that mean. On the x-axis right here, we have the position of the potentiometer, say between 0 degrees and 360 degrees for this rotary potentiometer. And on the y-axis, we have the resistance in percent, say in kilo ohms. Whenever we have a B-type potentiometer, or in this case B 10K, it means the relationship between the angular position, the angle, and the resistance is linear, which means the resistance changes linearly with the position. And that's great for most applications. However, for audio applications, what we need is a logarithmic relationship between the position and the resistance. And that's why we have another type, which is the A type or logarithmic taper type, which means that we have a logarithmic relationship between the position, or in this case for this rotary potentiometer, the angular position, and the resistance. And as we said, this is usually used in radios and for volume control, because our ears perceive the sound in a logarithmic fashion. Perfect. So this is it for the structure of the potentiometer. Now let us go ahead and check its circuit, how do we model it, and the equations behind its circuit. So, as we said, the output of a potentiometer can be read using an analog input pin on the Arduino UNO. And usually, the Arduino UNO R3 has 6 analog pins. Here they are labeled from A0 to A5. And these analog pins, they can be used to acquire analog signals, which are continuous time domain signals, and specifically between 0 and 5 volts. So we need to make sure that whenever we have a sensor, that its output is between 0 and 5 volts. If not, if we have a sensor that its output is in microvolts or larger than 5 volts, what we need to do is we need to build an amplification circuit using operational amplifiers in order to change or scale our signal in order to make it suitable to be read by an Arduino UNO. So let us go ahead and check the circuit. So right here, what we have is we have our potentiometer, which is connected to the 5 volts pin on the Arduino UNO. In series, this potentiometer is connected to a 1 kilo ohm resistor, as we can see right here and right there on the physical diagram. So we have the 5 volts connected to our potentiometer, the middle pin, and then we have the first terminal connected in series to our 1 kilo ohm resistor, and we will explain why in a bit. And we have the resistor in turn connected to the ground of the Arduino UNO, the 1 kilo ohm resistor. Now, the connection between the two is connected to the analog input of the Arduino UNO in order to acquire the change in resistance for this potentiometer. Now, we mentioned that for the potentiometer, we have 3 input terminals. And by itself, the potentiometer is a voltage divider, as we will explain shortly. However, in this case right here, we are using the potentiometer as a variable resistor, or in other words, as a sensor that its resistance change whenever it is rotated. So this is ideal for you to learn that we can replace this potentiometer with any other sensor that is resistive based. In other words, it can be a light dependent resistor or any other sensor that its resistance change with any input. You name it, whether mechanical, light, chemical, etc. So let us go ahead and learn a little bit about these equations. How did we derive them? And then code or build a LabVIEW code in order to interact with our potentiometer and control the brightness of the LED. So what we are going to do first, we are going to model the potentiometer to understand that, to understand how it works. So first of all, we have our potentiometer right here, and it's a variable resistor. So this is our potentiometer. This is our circuit. So let's call this one RP and say that we have this circuit. We have a 5 volts power supply right here. We have our potentiometer, and it's connected right there to the ground. Now, this potentiometer on its own is a variable resistor. In other words, it's as if we have 2 resistors connected in series. So let us go back to our slides. Whenever we said here that we can change the effective lengths of this resistive strip by moving the wiper clockwise and counterclockwise, but we are saying effectively that we have here one continuous strip, and this contact point in the middle is just dividing this strip into 2 parts. We have this part and this part. And essentially what we are doing, we are having a variable resistance right here by changing the length of the strip by rotating the wiper. So here we can model this potentiometer as 2 resistors in series. One resistor for this part or strip and another resistor for the other part or this strip. So in other words, it's a voltage divider. So this is exactly what we are going to do here by ignoring the 1 kilo ohm resistor that we have seen here. And now we are just modeling the potentiometer on its own for you to have a full understanding of a potentiometer and to understand that essentially it's a voltage divider. So here, in other words, for the potentiometer, we'll redraw it here as, or model it as a resistor. So RP, let's call it RP strip 1. And here we have RP strip 2. And this strip 2 is connected to the ground. The first strip is connected to 5 volts. And the middle strip right here is connected to the analog input pin. It can be connected to the analog input pin on the Arduino. Now, usually we don't advise you to do that. We do not connect, this is super important, we do not connect a potentiometer without a fixed value resistor in series to an Arduino. Because what happens is when we go to the lower bound, the resistance might get really small if it's a very good potentiometer, and eventually we will have a short circuit. So we never do that. We should always have in series with it a small value fixed resistor. So this is why we have the circuit that we have shown here in order to avoid a short circuit. But what you can do is you can connect these terminals or these two terminals here to a multimeter if you are curious and you want to see the change in values. So you can connect it to a multimeter and check the changing values. Now, this is the model of the potentiometer, which is equivalent to an RP with this arrow right here, meaning that we have a variable resistor. Now, what we are going to do next, we are going to derive these equations by having the 1 kilo ohm fixed value resistor right here, and essentially we'll measure the output right here. In other words, this circuit is ideal for measuring the resistance value of any resistive sensor. So let us go ahead and do that. So here what we have is our potentiometer RP, and we'll use only two terminals as we will see. Here we have our 1 kilo ohms resistor. Let's call it R. Okay, let us go back and check the labels. So it's called R just to be consistent. Perfect. 1 kilo ohm. And this is in turn connected to the ground. And here we have 5 volts. And what we need to measure right here is the output of the voltage divider and feed it to an analog input pin between 0 and 5 volts on the Arduino UNO. So let us do that. So in order for you to have a full understanding, since here we have the positive terminal and here we have the ground, let us redraw the circuit in a way that you can understand it. So here I can just redraw my power source from the Arduino as plus minus. Here I have RP. Here we have R, and this part right here is the ground, which is connected to the negative part of the power source. Now we know that we'll have a certain current here running through this circuit. Now what we can use is KVL, or Kirchhoff's voltage law. And what we can write is that we have minus 5 volts, and let's call this one Vs, minus Vs, because we're jumping from minus to plus the voltage across Rp, which is from Ohm's law, Rp times I, plus we have, according also to Ohm's law, the voltage across the resistor R, which is R, the resistance R times I, is equal to 0. Now we know that we have Rp plus R into the current I is equal to Vs. This means that the current I is equal to nothing but Rp, or Vs, over Rp plus R. Perfect. Now, what we are trying to do here, we are trying to measure the voltage, or in other words, the resistance across R. So we know that from Ohm's law, as we stated, that the voltage or the current right here, I, which is the same current across RP because we have elements in series, is nothing but, according to Ohm's law, V out over R. And remember that V out is the voltage across R, because this is the voltage that we are trying to measure whenever we vary RP. So this is equation 1, this is equation 2. Now all what we need to do is to replace 2 in 1. And simply what we will get is, by replacing 2 in 1, we get V out over R, is equal to Vs over Rp plus R. So this means that our output voltage can be expressed in function of the resistance values and the input voltage. So it's R over R plus Rp into Vs. And remember that Vs is fixed. It's equal to 5 volts. R is fixed, is equal to 1 kilo ohms. And Rp changes between 0, approximately 0, not exactly, and so approximately 0 and approximately 10 kilo ohms, because we have some variations as we will see. So now, by changing Rp right here, what we can do is we can change V out, and therefore this is a voltage divider circuit, because I can modulate the output voltage depending on the resistance value of Rp by changing its resistance value. So let us go back to our slide. We can check right here that we have the same equation. V out, which is measured using an analog input pin on the Arduino, is equal to R over Rp plus R times Vs. Now, using this equation, we can derive the expression of Rp if we want to know exactly what's the Rp value when we turn the knob clockwise and counterclockwise. And this is straightforward. So let us go ahead and do it right here. So all what we need to do, we need to use, let's call this one equation star. Using equation star, we can manipulate it in order to get Rp. So we'll have V out into R plus Rp is equal to RVS. Then we can write V out R plus V out Rp is equal to RVS. This means that V out Rp is equal to RVS minus V out into R. So this means that V out is equal to R into Vs minus V out over V out. So simplifying, we'll have V out is equal to R into Vs over V out minus 1. And now we can use this equation in LabVIEW, as we will see shortly, in order to deduce the value of Rp. Perfect. And this is it for the derivation. So now you fully understand what's a voltage divider circuit, how to derive the equation if you have any sensor that is placed here in place of Rp, whether it's a potentiometer or any other resistive sensor, and how to derive the value and how to connect the circuit in order to read the values using an Arduino UNO. So let us go back to our slides. So as we can see right here, the equivalent of this circuit, whenever we want to connect it to the Arduino, is as follows. We can see here that we are using only 2 pins of the potentiometer because we are using it here as a sensor by itself. And by rotating it, we are changing the effective resistance between these 2 pins, the middle pin and the first pin. So remember, if we go back to our potentiometer circuit, we are only connecting these 2 pins, and in series we are connecting this resistive element with the 1 kilo ohm fixed resistor value in order to simulate a resistive sensor. In other words, the potentiometer is a resistive sensor, because imagine that you have any rotating component connected to this rotating rotating element right here. You can measure the angle by correlating it to the resistance, especially if it's a linear type potentiometer. So here, as you can see, the middle pin is connected to 5 volts on the Arduino. The first terminal or pin on the potentiometer is connected to the analog input pin, which is the middle point right here, or the connection between the potentiometer and the fixed value resistor. And we have the second terminal of the fixed value resistor connected to the ground. And this completes our circuit. So this is the circuit for you in order to build, it to be able to write your LabVIEW code. Now let us go ahead write a LabVIEW code in order to acquire this data, the voltage. Also, in order to write this equation in LabVIEW in order to derive or find directly the value of the potentiometer in terms of resistance. And also what we will do, we will correlate this value in order to change or control the brightness of the physical LED. So let us go ahead and build our LabVIEW code. So we can just go to File, Open. For you, you will need to create a new LabVIEW file or VI. And let us place our block diagram on one side and our front panel on the other side. So as usual, what we need to do, we need to go to Hobbyist or Maker Hub in some cases. We need to open the connection to the Arduino, close the connection, and if we go right here to Peripherals, remember last time we used the digital folder or library right here. Right now what we are going to use is the analog because we are capturing a continuous time domain signal, which is an analog signal. So, and for this we have three options. We have write, read, and set reference voltage. For our case, our reference voltage is 5 volts because we are powering this circuit using a 5 volts, the 5 volts pin on the Arduino UNO. So we want to read a voltage. Perfect. So now we have our three blocks. Let's align them and let's place our analog input analog read block inside a while loop. Perfect. We have the COM port right here. It's COM4. It might be different for you. And for us, let us remember that our analog input pin, the pin that we are using currently, is the A0 pin. So we have 6 pins as we stated. So if we go back to our physical circuit right here, we can see that the connection between the fixed value resistor and the potentiometer here, this point right here on the breadboard is connected directly to A0, analog input pin 0. And that's why we need to specify here the analog input channel, and in this case, it's pin 0. Finally, what we have here, we have the voltage output. So we will directly get the voltage and not the resistance value, and the reference voltage, which is in this case 5 volts. The only thing that we need to read right here is our voltage output. So what we are going to do, we are going to call it V voltage output and say here in volts. Now what we need to add right here, in case we have any problem, we need to stop our code and we need to have a stop button as well. So we can hide its label right here. Cluster, unbundle. So let us maximize in order to have more space. Stop. Boolean or, so we need to stop our code either directly from the stop button or if we have any error. Finally, if we want to report any error message or handle it, we can just have a general error handler. And this is it for our code. One more thing we need to add here is a timer in order to make our code more efficient, and we'll specify 10 milliseconds. So this timer means that between each two loops, we will have 10 milliseconds of time. Just to avoid our while loop running as fast as possible, this will really help our CPU. We don't want to put too much demand on our CPU by running our while loop really, really fast. And you can monitor this using the index I right here of the loop. If we remove this timer, we can see that this index will go really will increase exponentially. However, if we put a timer here, we can see that it slows down, which means it consumes less computational power from our CPU. Perfect. So let us go ahead and try to run our code to see what will happen. So let us put our circuit on one side and our circuit on the other side. So this is our front panel. Let's run it. As you can see now, what we are reading is 0.92 volts. And let us try to rotate our potentiometer. As you can see, as I rotate now clockwise, the voltage is increasing until it reaches 4.99 volts. You can see it can never reach 5 volts because we don't have a perfect potentiometer that really changes between 0 and 10K. Sometimes it's below 10K, sometimes it's above 1K. It depends on the tolerance of the potentiometer. Same thing for the lower bound. We still have some resistance in the wires. We can see that the lower value right here is 0.48, and we need to make sure that these values are really for our circuit. So remember here that we don't have only the potentiometer, we have the 1 kilo ohm resistor in series. So therefore we can deduce these two bounds, the lower bound and upper bound, by plugging in here the values of 1K and the values of the potentiometer. And for Vs, 5 volts, as we will see shortly. So now what we need to do, since our circuit is working fine, what we can do is we can deduce the value or have an equation right here in order to check for the values of Rp. So remember that the equation right here is Rp is equal to R into Vs over V out minus 1. So the first thing we are going to do is to get Vs over V out. Our Vs here is the reference voltage. So if I just create an indicator right here for you to be able to see it. So let us put it there. Okay, reference voltage. Let's call it analog reference in volts. I just want you to see it. Let's run the code. You can see it's 5 volts. So I can take this analog reference value, which is 5 volts, and multiply it or divide it by V out, subtract minus 1, multiply everything by R, and we'll get to Rp. And remember, R is in kilo ohms. So let us go ahead and do that. So let us just make these the same size. So first of all, we're gonna need to have the divide right here, and I'm gonna divide V out. So let us Vs over V out. So we have Vs over V out minus 1. So I can just use the decrement here, minus 1 times everything is multiplied by R, which is 1000 ohms. So we can put 1000 if you want the value to be in ohms, or 1 if you want to display the value in kilo ohms. Create indicator. We'll call this one RP, and this value is in ohms. Perfect. So this is our code. Let us go ahead and check it. So as you can see here, we can replace it by silver just to have a uniform layout. And this is something very important. You should always have a visually nice and clear layout. Perfect. So let us run our code. So as we can see now, the value is approximately 8,900 ohms. If I rotate counterclockwise or clockwise, it's 0.9 ohms. So the lower bound is 0.9 ohms roughly, and we can see the voltage is 4.99. And if we rotate in the opposite direction, counterclockwise, we have roughly, let's just fix it, 9,000. It's around 10,000, but it's a little bit shaky right here. So due to the because of the breadboard, but that's fine. And we can see we have a value of 0.46 volts and 9,778 ohms. And in between these two values, we have the other voltage and resistance values. Now, something really interesting here that we can do is we can have a visual representation of our signal. And this is something really nice, and I always advise you to do so. So let us just place a graph right here, call it output signal. On the right hand side will display the voltage in volts, or we can have the resistance of the potentiometer, you name it. Here it's the time, but it's actually not the time, it's the index. So it's the amount of data points, because what we are dealing with here is a waveform chart. And for a waveform chart, on the x-axis, it doesn't display the time. Rather, it displays the index right here. So for every iteration or index value, it displays the output value or the voltage value. So that's why I called it the index right here. And here I can say I have the voltage versus index. And for all what we need to do right now is to have our graphical input connected to our voltage right here. So we can just place it right there. And what I like to do is to align these two and just move this one a little bit downward. And from there, everything looks fine. So let us now run our code again, minimize it. And now, as you can see, I can change the value and see the change graphically. So now if I change like in a quick fashion, I can see this what looks like sinusoidal wave, or I can have a step change, etc. So you name it. Imagine this potentiometer is connected to any mechanism or any other thing. Now what you can do here, you can play with the line style. I can change the color, I can have yellow, I can change the line widths, and I have other functionalities. So you can explore these by just clicking here on the plot and playing with it. Now, since I know that my voltage changes between 0 and 5 volts, I can also fix the Y scale. For now, you can see that the auto scale Y is selected right here, which means it will automatically scale my Y scale. But what you can do is you can unselect it and just specify 0 right here and 5 there, and you will have a fixed scale if you wish. Another thing that you can do right here is you can change the amount of data points that are displayed on the x-axis by changing or going right-clicking on the graph and going to change or chart history lengths. For example, you can increase or decrease the amount of data points depending on what you want. So as you can see right here, now I'm changing my voltage. Perfect. Now the final thing that we need to do is to really correlate these voltage values to a PWM or duty cycle value in order to control the brightness of this LED through the Arduino. So instead of connecting this LED to this circuit right here, we'll have two different circuits, and what we are going to do, we are going to correlate the values of voltage inside LabVIEW to a duty cycle voltage. So here's what we are going to do. We know that what we need is a block for the duty cycle. So we go to hobbyist, peripherals, digital, and digital right, or PWM actually, and we'll have here is a duty cycle. Now all what we need to do is to connect this one in series, this block, and let's recall to which pin our LED is connected. Our LED is connected, if we just zoom in right here, to pin 3. So it's connected to pin 3, perfect. So we need to select our PWM channel, create constant, and just say here we have pin 3. And for the duty cycle, we need to modulate this value between 0 and 1 by correlating it to the values of the voltage. So what we need to do is to go to mathematics, and inside we go to interpolation and extrapolation, and we choose the polynomial interpolation. Now for this polynomial interpolation, we'll create a constant for the y values. We'll have two values which are 0 and 1. We'll just make it a little bit larger. Perfect. We'll copy this one and we'll say for these we'll have the lower bounds of voltage and upper bounds. So let us run our code again. So if I rotate counterclockwise, my lower bound is roughly 0.463. So let's say 0.47. And my upper bound is 4.99. So let us put here 0.47 and here 4.99. And let us increase the size a little bit, and let's make these two the same size, roughly. Perfect. So we can still increase it a little bit. Right. Perfect. Now we need the X value. What's the X value? It's nothing but the voltage value. So voltage output. So this is our voltage output, and this is our X value. And all what we need to do, we need to connect this output to the input here for the duty cycle. So let us go ahead and check what will happen right now. So if I run my code, I can rotate my potentiometer counterclockwise and clockwise, and I can see the brightness of the LED changing now by modulating the angle. And imagine that instead of this potentiometer, you have any other sensor that its resistance changes with any stimulus. For example, light, pH, you name it. So now I'm going to stop it since it's working perfectly. And what we are going to do right now, we are going to test our linear potentiometer right here. So as you can see right here, we have this flexible linear potentiometer, and we are going to test it. So as you can see, it's quite flexible, and this is usually used for precision manufacturing or for control systems. If you want to build a ball and beam control system, you can use this one to locate this sensor to locate the position of the ball. So here we are going to use directly the potentiometer without a fixed value resistor. So here's what we are going to do. We are going to pick this 5 volts wire, as you can see right here, and connect it to one input terminal. Then I'm going to pick the ground wire and connect it to the opposite terminal. Then to the middle terminal, we are going to connect the input signal. So this brings us back to case 1, where we explained a voltage divider by itself as 2 resistors in series. So now if I place my finger on one point right here, I will have one strip on the right hand side and another on the left hand side. It's as if I have a voltage divider circuit with 2 resistors in series. So let us go ahead and run our code to see if this works. So let us run our code. And now I'm going to place my finger somewhere right here and slide it. And you can see that the resistance is changing by sliding my finger on the potentiometer. So it changes between 0 and 5 volts. Perfect. And this is it. You can now operate any potentiometer or any resistive circuit or resistive element or sensor using a voltage divider circuit. There's one more thing here, which is related to the LED. Once we turn off our code, we will see that the LED doesn't turn off completely, which means that we didn't set the duty cycle to 0 after we exit the while loop. So remember, to do so, what we need to do is to again have a block for the duty cycle outside the while loop to just set the duty cycle to 0 after we exit the while loop. And this is something very important whenever we're dealing with actuators. We need to make sure that we turn them off whenever we exit the while loop. Otherwise, they will be operating even after we stop our code. And this is something problematic, especially whenever you have motors operating or other actuators. So here we'll set the duty cycle to 0. And now, if we run our code again, let's check it right here. If we run it, so let us just minimize our block diagram, run our code and slide our finger, and we can see now that the brightness is changing. But now when we stop the code, we will see that the brightness of the LED is gone. In other words, the LED is turned off, and this is exactly what we need. And this is it for this tutorial.